everyone, welcome back to our YouTube channel. I'm Desire, and today we've got Uming, who has just completed the course ROS Basics with Python. So we'll first of all begin by seeing his presentation running on his code base running on the real robot, because we want to see that it works right. And then after that we'll get into the details about this project and see the slides and get a detailed explanation of what he did and how he managed to do it. Alright, so without further ado, let me hand over the platform to him so he can begin his presentation. Alright, whenever you're ready, Umi.
Yeah, so should I first show my show the real bot?
Yes, let's see that first so that you don't lose time on the real robot. Yeah,
sure. So I think let me run my project here. ROS Basics. Yeah.
Are you running it on a separate screen?
Running on what?
Are you running it on a separate screen, on a different screen? Because we still see your slides right now.
Oh, on another tab, but let me try to fix it.
Okay.
Can you see my
Not yet. We're still seeing. Maybe switch the tab you're sharing. Is it the same browser?
Yeah,
Okay, now we see
is.
it. Okay, now we see it.
Okay.
That's good.
Okay. So now I'm connecting to the robot.
Mm-hmm.
So now you can see the camera here. And now I'm going to execute my whole project.
Mm-hmm.
I will, oh, sorry. It's open a web shell here.
Mm-hmm.
And so it starts to following the wall.
Mm-hmm. I think there's a little bit of lag, but maybe we'll see it moving again.
Oh, it's lagging.
Yeah, just a little. Well, maybe it's also because the
It's
robot
too
speed.
slow.
Okay, there. No, it's fine. Don't worry. It was the cameras that were causing that.
Yeah.
All right. Can you explain to me why you chose such a slow velocity? Did you? Is there a reason behind that, or you just wanted to be safe?
Yeah, just be safe because there's no requirement on the velocity. So I just choose one that can smoothly following the wall.
Mm-hmm. Okay. All right. All right. Yeah, it's the same leg issue again, but yeah, there we go. Okay. Maybe it's on my side, but yeah. And now we can see it clearly.
Uh-huh. So in the terminal, it keep receiving the feedback from the action server.
Yes. All right. Did you use any type of controller, or it's just a efficient use if else loop?
I use PID controller.
All right. Yeah, it's really smooth. It shows.
Yeah.
Yeah, very nicely done.
Maybe I can raise up the velocity a little bit in the future.
No, it's fine. I think you are the designer, right? So you determine what you deem to be safe and correct. So it's not a it's not a big problem. I was just trying to understand the logic behind that. Yeah, behind that choice. Okay, that's good enough.
Now, okay, let me stop it.
Yep. So let's get into your slides so we can. You ran it in simulation, right? A couple of times, I'm assuming. And did you find any major differences there between the real robot and the simulation?
Yes, of course. Yes, definitely. So you can see some warning pops up here.
Yes.
Should I explain it now?
Your choice, but it will be nice for you to tell us about those differences, right? Just in passing, and then you can get into your slides as you go.
I will talk about it in my slides.
Cool. Okay, let's go for it.
Okay. So it's my honor to present you my project. It's about a wall following robot. And here is my content here. First, I'll walk you through the overview and task descriptions, and then I will explain the methodology about how I solve this problem and task. Yeah, and we've already seen the performance on the real robot. And this is the robot model that I'm using in this project. It's a Turtlebot 3. It's equipped with a lidar and several sensors for navigation. This is how the map looks like. It's a rectangular enclosed area and surrounded by white walls, and there's some irregular obstacles in the middle of the area. The first task is to find the wall. To do so, the robot should detect the closest wall and then rotate the face to face the wall and move closer to the wall. And after that, it should turn 90 degrees left and align with the wall. The second task is to follow the wall. There are some requirements. First is to keep the wall on the right side and maintain a small distance, and then it should adjust the angular velocity based on the laser data and turn left if the wall is in front of it. So the third task is to record the odometry. The odometry, the position of the robot and the oriental
orientation
angle should be should be recorded every second, and the action server should provide distance feedback to the client. And the record should be finished after one lap and return trajectory points. So next, I'll dive into the methodology behind all those tasks solutions. To find the minimal wall, I use the minimum range to find the closest wall, and meanwhile I use adjacent beams to help to exclude the obstacles. For example, here I find the minimum wall. I find the minimum range, but it's not the wall. And I compared I get the index, and then I compare the 30 um 30-degree behind and after the this range.
Okay.
If the values of the beams are approximately equal, then I would say it's likely the wall. Which
Okay.
here is not the case. So I will go for the next minimum range until I find um, a um, a a laser beam that has the
Those
equal
specifications.
value.
Right.
Yeah, yeah. So
Okay.
this is the
Very,
wall.
very, very nice method there. Okay.
Yeah. So
And
that
we'll explain too as well,
the
right?
mm-hmm.
Yep.
Yeah, and this is the detection part. After the detection, the program will continuously check if the robot is facing to directly to the wall and calculate how far is it the current facing direction deviating from the wall, and then turn left or right to minimize the error, and repeat until facing the wall straight. Yeah, and that's basically the first task. In the second task, which is the main the core um, feature of this robot, I used a dual error closed loop control. You can see I draw a diagram here, and you can see here we compared the set point, the desired distance, um, and compared it with the right distance here, and
Yes.
get error value. And this error value will be processed in a PID controller, which have the proportional term, a integral term, and a derivative term.
Right.
Yes, here, and but additionally, when I'm testing this, I find it is not sufficient. So I introduce um, a angular angular because I want the robot not only maintain the
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 distance.
distance, but also I want it to align with the wall.
Okay. So maintain orientation as well.
Yes, that's
Okay.
correct.
Okay.
So
That's
I
cool.
add,
That's pretty
yeah.
nice. Yeah.
So I introduce a proportional term to it, and some of these terms generate this angular velocity of the robot.
Very nice. Very nice.
Yeah, and the robot responds to this angular velocity and produce the distance here, and then I feed back to the loop again. So this is basically how the PID controller work here.
Very, very nice.
Yes, thank you. And then the third part is to record the odometry. First, the program initialized the action server to listen to the goal sent by the client, and and some variables that are used to track down the status, and also a subscription to the Odom topic. Yes, and after it received the goal from the client, the action will be triggered and entered to the callback function. The callback function consistently checked if a lab is finished by um, keep checking the x value and the y value compared to the starting point.
Okay. So there was a logging of the initial x and y values so that you would know that that was the
Yes,
beginning. Okay. Okay.
yes, exactly. And in the Odom callback function, we do those three things: is to take down, write down the coordinate and angle, um, and arrange it in a list, and then calculate the total distance, and then send feedback to the client that the whole the third task about. Yeah, that's basically it.
All
This
right.
is
All
yes.
right. Very, very nice presentation. Thank you very much, Uming.
Thank you.
All right. So now I want us to go back to your code base, right? Because I would like to ask you a couple of questions. So yes, you can switch to that tab now. All right. So
My
yeah, okay, that's good. Yes. So let's see the code. So first of all, what I want to ask you, it's probably gonna be very involved, but would you explain to me how you would do it, and also show me in your code base how you would change the behavior of your robot to start following the wall, but not keeping the wall on the right, but rather on the left, right? Because right now it went counterclockwise, right? Which means
okay.
yes, it was keeping the wall on the right. So how would it? How would you change your code to make it go the other way around, clockwise, keeping the wall on the left?
Mm-hmm. Um, so on the left, mm, if I want to keep it on the left first, um, the angular velocity should be changed. Oh no, this is find wall in the wall following.
Yes, yeah.
Um,
So yeah, it has to start from finding the wall, right? Because that's where the
ah,
whole placement of the wall starts. So yes, let's start there.
yes. So um, here, um, this is the function that determine whether it is a wall.
Mm-hmm.
And it's not changed. And the nearest wall nodes get back. No. Okay. Okay. So in this in the first task, what I am going to change is the final step to rotate to align the wall.
Hmm.
Um,
Okay,
here,
so is it okay? I see, I see. Cool. So
yes,
you're saying instead of rotating to keep the wall on the right, you'd rotate it to keep the wall on the left.
yes.
Okay.
So I just need to change this 180, the which means sorry, I got here,
Uh-huh.
which means this beam here,
Yes.
I change it to 540.
Okay. All right. All right. What happens to the laser scan data that you're receiving? What happens to the choice of indexes that you use in your controller?
You mean in the wall following task?
Yes, when it's now following the wall, right? So there is an index
Yes.
that you're constantly checking. What happens to that one as well?
Um, yeah, that because um, in my task, I find out that I I cannot use the 100. I cannot use the range with the index of 180
Uh-huh.
because when the robot is rotating, it for example, here in my slide here, because if I want, if for example the robot is facing in this direction here,
Yes. Okay. There we
and
go.
then and then the 180 index range will be here. So
Okay.
it's not the real right distance. So instead of that, I compute a little bit to get the real distance
Okay.
of the right.
All right. So, and
But
okay. Okay. Go ahead.
back to our topic here. Um, uh, I think I need to let me consider a little bit.
Okay. So, so let's say when your robot is completely aligned, right? When it's completely aligned with the wall, right?
Yes.
Um, there is a value you are using to check if the distance is within 0.25, right? that is a laser scan index, right? That checks how far the wall
Yeah.
is, right?
Yes.
And on what index, right? On what index is it on in your laser scan data? In your laser scan ranges data, what index is that?
Originally it's 180.
Right. So that would change. So that would change to what value?
To this 540.
All right. So which means that's the one that you constantly be checking, right? When your control loop is
Um,
checking for the 0.25 distance. Is that right?
no, that's not right.
Okay. So explain to me which one will be checked.
Um, so I compute. So please look at this line 69. I compute this right distance by
Yes.
sending two value into it. This is the right front distance and right back distance.
Mm-hmm.
Um, so and here, what I define this is that, oh, I can't say it. Right back and right front is here 200 and 210,
207. Okay. Okay.
and 400. It's not completely the oh, it's not. It's here, and where's right back?
There is right front angle. Then there
Okay,
is.
right back angle. Okay, here.
Okay.
Uh,
So.
150 and 210.
Uh huh.
These two value are it's near 180, but not the 180 itself.
All right, so they encompass your the distance. The one that
Yes.
you actually want, you are putting it in between those numbers, right?
Um,
S-
as I explained before, I use some um triangle function to calculate
yes.
the real distance.
Uh-huh. So in our case, right? So they would be flipped, right? So you'd have them
Yes.
between 360, the first one between 360 and 540. Is that correct?
I will change it to 550 and
Okay. And
these
570.
two values.
Exactly. Okay,
Yes.
that's what I wanted to understand. Okay, well done. You've answered exactly what I wanted to know. Okay. All right. So do you have anything else you'd like to explain in that case only before we get into the find all service? Or you're
Um,
satisfied with your explanation right now?
um, yes, like, but here I use some I use some because when it's rotating, I let it turn fast when the arrow is big,
Mm-hmm.
and let it turn slower when the arrow is slow because sometimes it turned too fast and
Mm-hmm.
it overturned, and it had to like adjust and keep vibrating near the target.
Mm-hmm. So this computation of angular velocity is outside of your control loop, right? So you yet
Uh,
it is not
there,
being handled
yeah,
by the PID controller.
no. The PRD controller only used in the wall follow.
I see. Okay, so this is mainly for when you want to turn the corner, right?
Oh no, this is the in the find wall service when the robot
Oh,
is trying to
to
face
align.
to the wall,
Mm-hmm. Mm-hmm. Okay.
and yeah, yes.
All right. All right. That's all good. But anyway, very clear explanations. I really like the flipping around of the angles that you now consider when you're doing the whole following in the reverse direction. So that's very very well explained. And I had to probe you to go in that direction because I think it is very important. Given your implementation, it is also important to understand how it would change when you want to change the behavior of the wall following. So that's very nice. So well done on that bit. And I think let's wrap it up here. It's been a very nice presentation, and a warm congratulations to you, Uming.
Thank you.
Alright everyone, this was Uming's presentation and a warm congratulations to him, and very wonderful explanations, very illustrative slides, and would like to encourage all those of you who would like to take up this project to do so, and you can come and showcase your work here. So until next time, keep pushing your learning. Bye bye.